Hello and welcome to lecture 35 of the course Theory of Computation. In the previous couple of lectures, we saw decidable languages arising out of regular languages and context-free languages. So now we will try to understand undecidable languages. So we'll try to see like undecidable languages, but before we can prove that these languages are undecidable, we'll have to build some theories, right? So if you think about it, to show that something is undecidable, it's not clear how to show it. So basically, you have to say that there are so many approaches in which you could possibly decide a language, right? And you have to rule out each and every one of these approaches, right? So how do you possibly show that no Turing machine is able to decide this language, right? So that is really a challenge, and it is not so straightforward. So in order to get there, we will have to actually build some theories, right? So the language that we will show is undecidable is this acceptance problem of a Turing machine, ATM, right? So given a Turing machine M and a string W, the question is, does M accept W or not, right? So this happens to be somewhat tricky to build a decider for, right? And we'll show that this is in fact undecidable. So before getting into decidability, is this Turing recognizable, right? So if you think over it for a bit, you'll see that it is Turing recognizable, because what you can simply do is run the recognizer will just simulate the machine M on the string W. Okay, so run the machine M on W, right? Now if M accepts W, this will you accept. If M rejects, you reject. But the problem is that this is not a decider. This is because if a decider has to accept if M accepts W and reject if M does not accept W. But if M loops on W, right? If M does not reject W and M does not accept either, if M loops on W, there is no way this machine will get to an outcome, right? It will also continue to loop, because what we are doing is simply running M on W and then just reporting whatever the outcome is. So if M loops on W, this is not going to reject, but a decider for ATM has to reject M comma W if M does not accept W, right? But this is not a decider, since it may loop if M loops on W, right? So that's why it's not a decider, right? However, it is Turing recognizable, right? Now, as I said before, to actually show undecidability, we need to set up a bit more theory, and let's get to that. So the first point that I have to cover is that of bijection, right? And Sipser calls it correspondence. It's not really that hard a concept. It's something that many of you may have already learned in your school, or maybe in your school possibly. So bijection is a function. It's a mapping from one set A to another set B, right? So it's a mapping from one set to another, mapping from let's say A to B, and it has two properties. One is that it is one to one, right? And the second is that it is on to. So by that, what I mean is a mapping from, let's say let's say I have two sets, S1 here and S2 here, right? So S1 is the set on the right side and S2 is the set on the left side. So let's say this is S1 and let's say this is S2. Now for every element in S1, I want to identify a map. So this is the map F, right? So every element in S1, I want to identify an image on the S2. So so here A has an image, right? A has an image, B has an image, C has another image, right? So what do I mean by one to one and what do I mean by on to? One to one means no two elements from S1 can have the same image. So if you see here, that is indeed the case. Like you take any two elements of the of the left side, they don't map to the same right side element, right? So this is one to one. On to simply means that all the right side elements are covered, right? There is no element in the right side which is not an image, right? So maybe I'll just define it very briefly. So one to one means fx is not equal to fy if x is not equal to y, right? So the only way two elements can have the same image or is if the two elements are indeed the same, or let's say it's a very twisted way of saying it. So basically two distinct elements x and y, if x is not equal to y, their images are also going to be different. And onto means so maybe over here I will say f of s1 to s2. All the elements in S2 are an image of some element in S1, meaning every element in S2 has a pre-image. So you pick any x from S2, there is some, or you pick any y from S2, there is some x in S1 such that f of x1 is equal to y, sorry, f of x is equal to y. So which means that there are no elements here which are not an image of an element in S1. Right. So this is what onto means. And one to one and onto together means it's a bijection, and it's actually a nice set of properties. So we have two sets here, S1 and S2, like that I have pictorially drawn. Right. So notice that if I had, let's say, S2 had, let's say, one more element, okay. Now we cannot have a bijection between S1 and S2. This is because there will be an unequal number of elements in S1 and S2, and however which way you try, the one element in S2 will not be covered. Also notice that suppose there was one more element in S1, even then it will not be, you cannot get a bijection, because there will be one extra element in S1, and consequently you will have to have two elements in S1 mapped to the same element in S2, right? So the one to one property will have to be violated. So what I am saying is that you can have a bijection from S1 to S2 if and only if it is of the same size, right? And this is very easy to see for finite sets, right? So maybe just write this here. We can have, okay, maybe in fact I don't have to write it, I have already written it already. There is a bijection from S to T if and only if the size of S is equal to size of T. Right? Size of S is equal to size of T, and this is pretty clear, right? So maybe you can just to give another example, let's try one more thing. So let's say 4 elements here, 4 elements here, you can have a bijection, right? So let's say 1. This is a bijection, right? And you cannot have a bijection if the sizes of the sets are different, right? So for instance, I've written one more example here, is if you have a set of 5 apples, this set can have a bijection with the set 1, 2, 3, 4, 5, right? So you can map one apple to number 1, another apple to number 2, and so on, right? So this is the point of bijection. So bijection means it's a mapping from one set to another with the properties 1 to 1 and onto, right? And we can only have it if the cardinalities of the sets are the same. Now this is all easy to see when we are dealing with finitely sized sets. Now we want to extend this notion to infinite sets, right? So yeah, we want to extend this notion to infinite sets. So we want to say that even for infinite sets, let's say A and B are infinite sized sets. We want to say that A and B are of the same size if there is a bijection from A to B, even though they are infinite size sets, right? So we want to extend this notion to infinite sets, and that's where the definition of countability comes into picture, right? So we say that a set A is countable if there is two possibilities. One is that it is finite, and two is that it has a bijection with the set of natural numbers n, right? So a set is A is countable if it is finite or if it has a bijection with a set of natural numbers, right? Set of natural numbers is simply 1, 2, 3, 4 up to infinity, right? 1, 2, starting from 1, right? So the word is countable. So why do we say countable? Because so suppose it has a bijection with n, right? So which means this is maybe I'll just draw it horizontally. So this is n, right? 1, 2, 3, 4 and so on, and there is another set, let's say some set S. We want to say S is countable, meaning there is a bijection from n to S, right? So which means 1 is assigned to some element here, 2 is assigned to some element here, 3 is assigned to some element here, 4 is assigned to some element here, and so on, right? And every element in S is mapped to some element in n, or n is mapped to some element in S. So in other words, we can think of, basically we are calling one element as the first element, right? So this element is the first element, this element is the second element, this element is the third element, and this element is the fourth element, and so on. So basically we are, in a way, we are kind of labeling elements in S one by one. So this is first element, this is second element, this third element, this fourth element, and so on. And every element in S, so you consider any element, let's say you consider this element in S, it must be mapped to some number here. So maybe this is the 100th element, maybe, right? So every element in S has to have it has to feature in this listing somewhere, right? If it does not feature, that means it does not have a pre-image in n, and that means it is not a bijection, right? It will not be onto. So every element features in this listing somewhere. So basically you can take the set S and you can count elements one by one. This is number 1, this is number 2, this is number 3, this is number 4, and so on. This is what I mean by countable, right? Initially, on the first glance, it may seem that this is a fairly trivial thing. Even if it's an infinite sized set, I should be able to move one element at a time and say this is first element, this is second element, this is third element, and so on. But it turns out that it is not so common. In fact, most of the sets that we have, that we know, are going to be uncountable, right? So being countable even amongst infinite sets, it's a very, very special property, right? So we'll see why it's a special property. So the reason, so I'm hopefully at this point it's clear why it is called countable. Basically, you have an infinite set and we can count it. This is first element, this is the second element, this is the third element, and so on, so that none of the elements of the set are missed out. All the elements appear some point in the ordering, right? So you want to list out a set is countable if it has a bijection with n, right? Or we can say you can list out the elements of the set one by one so that no element is missed out. So it's like you're counting. This is the first, this is the second, this is third, and so on, right? This is what I mean by the word countable, right? So example, so n itself is countable. So if it's not clear so far, so any set has a bijection to itself, right? So this is n, right? I can have a identity mapping. So the first element is 1, second element is 2, third element is 3, and so on. So n has a bijection to itself. You map every element to itself, right? So all elements are covered. Now let's consider a slightly different thing. Consider the set of even numbers in n. Let's say 2, 4, 6, 8. So on first glance, we may think that we cannot have a bijection, because clearly this set, so this is n, this is let's say even numbers in n. This is only half the numbers in n. We are only collecting the even numbers in n. So one may think that you cannot have a bijection, but that is wrong, because I can have a bijection like this, right? I can map an element 1 to 2, and element 2 to 4, element 3 to 6, 4 to 8, and so on. So basically every element I is mapped to 2 times I. So 2 is the first element, 4 is the second element, 6 is the third element, and so on. And I can list down all the elements in the second set. Maybe I'll call it E. So all the elements in E are mapped like this, and it's clearly 1 to 1. No two elements x and y in n get the same image, and it's also onto. No element in E is missed out. So this is something that is surprising with infinite sized sets. So even though we thought we were dealing with a set that is half the size of n, it happens to be of the same size as n, right? Same size as n in the sense that there is a bijection with n, and that is going to be our definition for two sets having the same size, right? Clearly it works for finite sets, but what we are going to say is that even for infinite sets, we will say that two sets have the same size if there is a bijection between them. So E and n have the same size, even though E is like half the elements of n, right? So this is something that happens with infinite sets. So maybe now the next thing is consider n squared. So by n squared I mean like the grid. So this is 1, 2, 3, 4. So I'm talking about all the pairs. So by n squared I meant all the pairs x, y, where x and y are in n. So I can talk about the grid kind of thing, like that what we have here. These are the grid points are the elements of n squared. So now this looks like even more, it looks much bigger than n, because the number of points in n squared seems to be the square of the number of points in n, right? Because it's a Cartesian product with itself, and Cartesian product usually multiplies the size. In fact, so one may think that n squared is of much bigger size, but it is not. We can actually track the elements of n square in this following way. So you start with 1, or you start with 1, 1, then you go to 1, 2, then you go to 2, 2, then you go to let me just say it, 1, 1, then you go to 2, 1, then you go to 1, 2, then you go to 2, 2, right? Did I do it right? No, I didn't do it. So you can do this kind of thing. So you can start with 1, 1, then you go to 2, 1, then you go to 1, 2, then you go to 1, 3, then 2, 2, then. So basically what you are doing is you first take all the pairs which add up to 2, which is just 1, 1, then take all the pairs adding up to 3, which is 1, 2, and 2, 1, then take all the pairs adding up to 4, which is 1, 3, 2, 2, and 3, 1, pairs adding up to 5, which is like 1, 4, 3, 2, 2, 3, and so on, and pairs adding up to 6, and so on. So basically you are covering from the point closest to the origin in ways like this. So this way all the points are covered, and no two points get the same mapping, hence it's 1 to 1 and on to, right? So with infinite sets, even sets that are seemingly, okay, so this is important, seemingly bigger can be the same size. This cannot happen with finite sets, right? Then the next thing I want to talk about is integers. Let's say Z is the set of integers. So let's say this is the set of integers. Right, so you have 0, 1, minus 1, 2, minus 2, and so on. And in fact, there is a clue as to why it is countable just in the way that I am writing it. You could start from, you just want to check, map everything, right? You start from 0, then you go to 1, then you go to minus 1, then you go to 2, then you go to minus 2. So you can start from the center and they kind of spread out. 3, minus 3, 4, minus 4, and so on. So all the positive as well as negative numbers are all, positive as well as negative integers are all covered. So Z is also, the set of integers is also countable, right? So Z is a set of integers, set of all integers, not just natural numbers, positive as well as negative. And in fact, the set of all rational numbers is also countable. I am not going to explain, but it is similar to the n square thing, because rational numbers can be thought of as like a ratio of two integers, p by q, right, p and q, and then you can enumerate p and q as like this, as a grid or something, and then you can count them one by one, right. So natural numbers is countable, even numbers in n is countable even though it's seemingly smaller, n square is countable even though it's seemingly bigger, set of all integers is countable, a set of all rational numbers is countable. So then I already said that being countable is a sort of a special property, but so far whatever we saw has all been countable. So one may naturally ask, show me something that is not countable. So the set of real numbers, set of all real numbers, right, the set of all numbers on the real line, this is uncountable, right, and it's not a very difficult thing to see, but it's a very clever idea, right. So just think about it. You will have, like I said about decidability, like to show that something is undecidable, you have to rule out all possible Turing machines. To show that something is uncountable, you will have to say that whatever way you try to list it, you try to map, okay, this is the first element, this is the second element, this is the third element. Whatever way you try to list down the elements of R, you cannot list them down like that. Somehow or the other, some element will be missed out, right? For other sets that we saw, like n square or q or z, we were able to list down all the elements of that set without missing out on any of them. But for R, to show that R is uncountable, R is a set of real numbers, you have to show that whichever way you try to list down the elements of R, you cannot capture all of them, right. So the way the proof goes is the following. So you assume that the statement is false. Suppose R is countable. So then that means that if R is countable, there is a bijection. Okay. So from the bijection, we will get to a contradiction. So let there will be a bijection from n to R, right. So from the natural numbers to real numbers. So here we list down the bijection. Let's say the first number is, let's say, 1.23423. Okay. So I am putting multiple decimal, like it could be, in general, it could be an infinite, it could be an infinite thing after the infinite sequence after the decimal point. Let's say 2 is 3.14159. Okay, so this is kind of the number pi. 3 is 5, the third number is 5, just the number 5. So I just put 0000, right. Suppose we can list down the bijection in some manner, right. So now from this we will derive a contradiction. right? Suppose R was countable, what does it mean? It means that you can list it down like this, right? Now we will show that whatever be the listing, so this is some arbitrary listing, we can get some number that is missed out by this listing, right? So like when we showed that something was countable, like Z was countable, right? So this when we showed that Z was countable, we are actually capturing every number in Z, like starting from 0, 1, minus 1, 2, minus 2, all the numbers. So if you ask me where does 100 come, I can tell you, okay, 100 is going to come at this position. Whereas here, we are not, that's not going to happen. We can show that numbers are going to be missed out. So let us see how. So let us construct a number x, okay. So the speciality of the number x is this, okay. So what I will do is that, so the first x is going to be 0 point something, okay, and it's going to be something between 0 and 1, and what I will do is this. So look at the first number after the decimal point of the first digit after the decimal point of f1, right, which is 2. Look at the second digit after the decimal point of f2. Look at the third digit after the decimal point of f3, fourth digit after the decimal point of f4, fifth digit after the decimal point of f5, right. So what we will do is, when writing down x, so I know the first digit of f1 is 2, so I will write 3 here, okay. So the goal is that x is going to be different from f1 because the first digit after the decimal point is different from the first digit after the decimal point of f1. Now second digit of the second number is 4, so I will write, let's say, 5. Third digit of the third number is 0, so let me write 1. Fourth digit of the fourth number is 3, so let me write 4. Fifth digit of the fifth number is 0, so let me write 1. Right, so I've written something. So now the way we constructed x, right, so the first bit after the decimal point is 3. Now that makes it different from f1 because in f1 the first bit after the decimal point is, first digit after the decimal point is 2. So x differs from f1. X differs from f2 in the second digit after the decimal point. It is 4 here and it is 5 here. X differs from f3 in the third digit after the decimal point, and so on. So the way it is constructed, we are making sure that x is not the first number in this listing, x is not the second number in this listing, x is not the third number in this listing, and so on. So you and x is infinitely constructed, right? Like I will keep filling up. So this is a theoretical listing that we have, or if R was countable, there is a listing, and now x also has infinite numbers, infinite digits after the decimal point, right? So now you ask me, is x same as any number in this listing? No, because let's say you take the 50th number in this listing. Now x will differ from the 50th number in this listing in the 50th digit after the decimal point. X will differ from the 100th number in this listing in the 100th digit after the decimal point. So x is going to be different from all the numbers in this listing. So which means we have discovered an issue in this listing. If this listing indeed covers all the real numbers, how come x is not captured? Right? So that's the contradiction. So the fact that we are able to produce a number which is not in the listing is the contradiction. Right? And one small thing to note is that sometimes we could have like two numbers with different digits equal to the same number, like say 5.000 and 4.999. This actually denote the 0.999 actually, like 4.999 actually it's equal to 5, right? So when I am choosing the digits of x, I just take care to avoid 0 and 9, which is okay because we have 10 digits. So which I have taken care here. So the digits of x are not going to be 0 or 9, so that this situation does not arise, right? I don't want, if I choose, let's say 999 or something in x, then it may accidentally be equal to some other number in the listing. I don't want that. I want x to be distinct from all the numbers in the listing. And so we choose whenever we choose the ith digit of x, we choose something which is not 0 or 9, and also which is not the ith digit of the ith number, right. So we produced a number x which is so x is clearly a real number, right. So x has infinite digits after the decimal point, but it is a real number, but it is a real number that does not feature in this listing. So which means the listing is not thorough or listing is not proper, right. So hence it means that the assumption that R is countable, if R was countable then all numbers would be listed. So this means we produce a number which is not in the listing, which means R is not countable, hence R is uncountable, right. So I think we have already reached half an hour, so I think I will cover the next topics in the next lecture. But just to quickly recap what we saw in this lecture, we defined what is bijection. Bijection is a mapping from a set to another set, which is both 1 to 1 and odd to. And the reason for using bijection is that in finite sets we can have a bijection from one set to another if and only if they are of the same size. Now we want to extend this notion to infinite sets. So a bijection of an if a set has a bijection with the set of natural numbers, we call that set to be countable. And now we saw that the set of all natural numbers, obviously it is countable because it has a self like bijection. Then we saw that the set of even numbers, even natural numbers, set of n squared, where n is a set of natural numbers, the set of all integers, set of all natural numbers, set of all rational numbers, these are all countable. However, the set of all real numbers is uncountable, and that we use this clever argument where we assume a listing and list down all the numbers, and we choose x to be different from each of the numbers in the listing. So one point that I missed to say earlier is that this proof technique is called George Cantor, C-A-N-T-O-R, diagonalization argument. So this technique is called diagonalization. So it must be evident why it's called diagonalization, because we have the listing and then we choose x so that it differs from all the diagonal entries. So the first entry in the first number, second entry the second number, third entry the third number, and so on. So we choose x to be different from all the numbers in the diagonal. So because of that, it is called the diagonalization argument, right. Hence R, the set of all real numbers, is uncountable. And with that we complete lecture number 35, and in lecture number 36, in the next lecture, we will continue to build towards the theory of undecidability. We will try to build, we will first show that there are undecidable languages, then we will actually see which one it is. In fact, we have already told which one it is. It is ATM, the acceptance problems in Turing machines. Anyway, that's all for lecture number 35. See you in lecture 36.